All right, so today we're going to take a look at 7.2 volume, and we're going to look at something called the disk method. This is the title for the section, but we're actually going to look at two methods. One's called the disk method, the other's called the washer method. And what I want to first talk about is the general idea of what's going on. So the idea is that we're going to take what we know about area, like the integration idea, finding an area between curves, the areas under curves, things like that, and what you know about volumes, like from geometry, and combine these ideas. So imagine taking a two-dimensional shape, like some of these trapped slivers that we were working with last class period, and spinning them around some axes. Okay, so I'm spinning them around some different lines. The image that you get is called a solid of revolution. Okay, and then the line that you spin it around is called the axis of revolution. Okay, and so it may be vertical or it may be horizontal. We're not going to work with anything that's diagonal, just verticals and horizontals. And the simplest such object is a disk. And this is the idea of what we're doing. And so there's a couple different YouTube videos that I'm going to do, and they're posted out in Moodle Rooms too if you want to rewatch them, because this video that I'm recording right now will not record their video at the same time. It's going to pause this one. We're going to watch theirs, and it'll pick back up when I get back in the program, okay? Okay. All right. Let's do it this way. All right, so we're going to pick back up where we left off, and there's a few things that he mentioned in his video that we're going to fill in here. So the first thing that he talked about was cylinders, remember? What we've actually done or are going to be doing whenever we're creating these is a bunch of little bitty cylinders. And because they're really skinny, we'll sometimes call them discs. So sort of imagine like a hockey puck. They're a thin cylinder, really short and squatty, okay? But what was the volume of a cylinder? What did it say that one was? Do you remember? You should know just from general knowledge. What's the volume of a cylinder?
2 pi r.
There's no 2.
R squared.
There's a pi, yeah. Pi r squared times the height h. Okay, so the pi r squared gives you the area of a circle, basically, because that's the area of a circle formula, and then you multiply it by h, that gives you the height of a cylinder. H is the height of the thin disk, or the disk of the thin cylinder. But as we let h go to 0, we have, this is where my notes would be in handy because I don't have it written in for you. Does it say anything on yours? Just have a blank. Oh, there just needs to be a colon here. We have the disk method. There we go. So the disk method volume, and so he gave you I don't know if he actually wrote it down explicitly, but he used it several times. So the volume is going to be pi times the integral from a to b. And he wrote each of these at different points. One of them is that r of x squared dx. So if you have something that you are rotating around a horizontal axis, so you might want to jot a note to yourself that this is what we're going to be using with horizontal lines or horizontal axes of rotation. And we're going to be using this formula. And you can see the description of, or the formula for the volume of the cylinder sort of hidden within there, right? You've got the pi, you've got r of x squared, that's a radius squared, and then just like he talked about, that dx is actually the width or the height of your cylinder, okay? And then, of course, the other one that he wrote and that we will have to be able to use as well is rotating around a vertical axis. So this is the integral from, and I'll call it c to d just so that it's recognized that it's different numbers. And this would be r of y dy, and the r of y is squared, just like the other one. So this one is used on your vertical axes of rotation. R of x or r of y, like we've said, is the radius, and the equation is in terms of x or y that we are spinning. So we're rotating or we're spinning this object around an axis, okay? Now, we're going to do an example. This is the first one, and you'll notice this is similar to one he did. We're rotating it differently than he rotated this example. But this example is y equals square root of x. What you're going to find is that it's often helpful. In fact, I would highly recommend and encourage you to do so because I'm going to be looking for it, for you to start by drawing the equation you're given. And if you don't know particularly how to draw one, your calculator can help you do that, of course. The equations that you're going to be given are not going to be terribly complicated equations, generally speaking, okay? So they're not going to be something just totally out there. So this one's really nice and clean, and it looks like this, more or less, right? And you're told up here that you're supposed to go between these three curves. So the first curve, y equals square root of x, I did that one. Where is y equals 0? Which one is it? It's the x-axis, right? Yeah. So we're trapping ourselves by the x-axis and this curve, and x equals 3. Where's x equals 3? That's a vertical line, right? At 3. So I'm going to draw this down right here. Here's my x equals 3. Here's the lower one. This is y equals 0. And then here's my curve up here, square root of x. All right, is everybody with me? Okay, so we're actually going to be taking a look, and our graph, depending on whether we're rotating around x or y or whatnot, needs to know where the image starts and ends with respect to the x values and with respect to the y values. So this is the picture that we get. And of course, we're trying to take this image and, like we were talking about in the video, draw a representative rectangle. Now, I'm drawing my representative rectangle like this, and the reason I am is because it tells me that the x-axis is the axis of revolution. So I'm going to spin my graph like so. And your representative rectangle is always perpendicular to the axis you're spinning around. Okay, so you're drawing a perpendicular little segment whenever you're drawing this. Okay? All right, so we're going to create an integral. This is the volume we're looking for. The volume is pi. It's times the integral from what to what? Well, it depends on what we're integrating with respect to. So are we integrating with respect to x or y here? X. How come, Hannah? Yeah, exactly. The x-axis is the key. It's a horizontal axis. And in his picture, which was really nice, I don't have the ability to write quite as small as he did. He talked about the fact that this right here is dx, right? It's a little bitty sliver in terms of x. So this is in terms of x, so I do have dx. And I need to know that because I need to know what my limits of integration are now with respect to x, not y. Well, with respect to x, I go from 0 to 3, right? So I've got 0 on the bottom and 3 on the top. And then my radius needs to be what would be in this picture, sort of the height of this. It's a terrible notation because I've already got something else I called the height, but it's the radius, how far from the axis I'm going out to rotating. So imagine if this thing was rotating, where would the radius be? Well, it would be from the center out. And that's the height of this rectangle that I've just drawn, right? Well, the height of that rectangle is my equation. It's y equals square root x, okay? And I need it in terms of x, so square root x is the correct notation to put here. But I like square rooting squares. I like squaring square roots, let's say it that way, because that's really nice. What happens when I integrate this? Or what happens when I simplify this before I integrate? Is it? It's just x first, right? And then I'm going to integrate. So when I integrate, what do I get? Integral of x. Thank you. X squared over 2. I'm evaluating at 3 and 0, and evaluating at 0 is super extra duper friendly because in a lot of the functions we're going to deal with, just like the one you saw the video on, the 0 ends up being 0 when you plug it in. That doesn't always happen, and you don't always have a 0, but when it does happen, it's very nice. So I'm going to plug my 3 in, so I have 3 squared over 2, and then I'm going to plug my 0 in, so I have 0 squared over 2. So what is 3 squared over 2? It's 9 over 2, right? So, and then I've got the pi on the outside, so this is 9 pi halves. Is that all right? Now, what you're going to notice in this section is that the hard part is getting the problem set up. The integration and the plugging in values and whatnot at the end, typically speaking, is the simpler part. We're not doing integrals that are extremely complicated, okay? But the setting things up can be complicated depending on how visual you are when you think, all right? So we are going to do one more video. Some details. So we watched the washer method video, and we can take this idea of discs, just like he talked about, and extend it to washers. The method's almost identical, right? The formulas are also very similar, yeah? So for a image for this, you could maybe, when I saw his pictures, I'm thinking toilet paper roll or paper towel roll, right? You got a cylinder on the outside, and you've got the empty hollow cylinder on the inside. And we're wanting to figure out, how much paper towel is on there or whatever. So when we're taking a look at the volume we end up getting is going to be pi, and then we had r squared minus little r squared times our height. And as we let h go to 0, right, the height go to 0, become infinitely smaller, having infinitely many washers, then we end up getting the volume method for our formula. And I'm just writing one of the two of them down. He actually wrote everything down in terms of y. I'm going to write it in terms of x. It's identical, just different letters. So our volume actually ends up being pi times the integral from a to b. And we have the radius, the outer radius squared, minus the inner radius squared. Doesn't look very good. Let's try again. And then all of this with the dx on the end, right? The dx is like my height. Okay. And then, of course, I can have the same issue that I did on the other slide where I do it with respect to y. So everything is done with these perpendicular rectangles. It's important that you draw the image correctly so that you can get it set up correctly. Because if you don't get it set up correctly, there's no chance of getting the right answer, obviously, right? So the biggest discussion here is going to be the setting up of the description. So if you'll notice, all of my examples are going back to the same equation from the first one. In fact, this is letters A, B, C through, what do you go through? H? No, that's not through, that's too many. F, E? How far do I go, Dylan? What's the last one? I think there's 5 of them. So E? E. So we're going to go through E. In all of these cases, I'm using the same equation, okay? Because I don't want you to be focusing on drawing a different equation here. I want you to see what happens when you're rotating on different lines. That's the focus. Because that's what's going to change these radius that's coming apart, coming about by doing that. So my graph is going to start out the same on all of these, okay? Because the other part of this is what I'm wanting to focus on. So my graph, same as before, is going to have this curve going from 0 to 3. Okay? So I'm coming out here to 3, up to square root 3, and I've got this image on the inside, right? And this is getting rotated around an axis. Now, the axis that we're going to rotate around in this question is the y-axis. We just did the x-axis a moment ago. So here's my y-axis of rotation, yeah? And I shouldn't have drawn something I did before. Let's try this again. We're going to draw it correctly. I need to fix one more thing. It does go out to 3. This is my image that I get when I rotate. There we go. And that's based on the fact that I'm rotating on the y-axis. So let's get that drawn correctly. Sorry about that. So he drew a picture similar to this, right? Yeah? Yeah, he did. So we're rotating, using the y-axis as the axis of revolution. I drew it right to begin with. I'm just messing things up all over the board today. I had the picture I wanted to begin with. I'm thinking of another image we're going to do in a moment. I'm sorry. I hope you're using pencil. You're supposed to be, right? Okay, let's do this. There we go. This is right. Cameron, you should be using pencil. I know I had to take notes in pen too. Okay, so we're rotating this around this axis. We have the integral that we're going to set up. It's got pi in the front. This is my volume. Now I want to draw that representative rectangle. So when I draw my rectangle, where is my rectangle going? What is my rectangle going to look like? A vertical rectangle or a horizontal one? Horizontal. It's going to be long and skinny horizontally, right? This is my horizontal rectangle. Yeah? Something like this. So as you can see, just like what he talked about, this is actually delta y. Yeah? And what that means, in reality, is that I don't have any equations expressed in terms of x anymore. So this equation up here needs to be solved for x so that it can be written in terms of y. So if I solve this for x, what does x equal? Y squared. So that will help me with my radii. I've got two radii to find here. I've got an outer radius and I've got an inner radius. I think red might work. So my outer radius comes all the way out here to my vertical line that's dropped down. What is my outer radius on this picture?
3.
It's 3. So I take my outer radius and I square it. This is different than the picture he did, right? Yes, it is. And the next one that he did then was the inner radius, and we will as well. So my inner radius is right here. My inner radius actually goes from my y-axis to the curve itself. And that distance right there is the equation of the curve. It's x, yeah? That's my x distance. And x, in this point where I stopped, is equal to y squared. So this right here is x, which is equal to y squared. So then this is minus y squared. So far, so good? All right. And we'll clean that up a little bit too. So we have pi. Oops, I didn't put my limits of integration. What are my limits of integration here? 0 to square root of 3. Why square root of 3, Cameron? Yeah, it's because we're doing everything in terms of y, yeah? So it's the y-axis that tells me my limits of integration. All right, so we're going from 0 to square root of 3 of 9 minus y squared dy. And what is the integral of 9 minus y squared?
9y minus y to the third over 3.
Okay, so after all the more difficult integrations that you did in the last test for me, these integrations are not going to be difficult, okay? That doesn't mean there might be not something that's a little bit more challenging than this, but they're not by and large challenging integrations. The challenging part is the setting these things up. So we're going to plug in square root 3. So I have pi. And then I have 9 square roots of 3 minus the square root of 3 cubed over 3. And then minus 0. If I plug 0 into each of those, I get back 0, right? 9 times 0 is 0. 0 cubed over 3 is 0. So I don't have anything from there. All right, can you simplify square root of 3 cubed over 3? What would that be? It would be, you're close. It will be just square root of 3. Right, so square root cubed means that I'm going to have 3 of those underneath the radical. Do you guys remember doing this back when you did radicals? So you're looking at me like you don't know what I'm talking about. So when I have this cubed, this means I have 3 of these guys. And 2 of these multiply, add together, and they give me back 3, right? And that will cancel with a 3 in the denominator. So we're all good with that? Okay, so I really have 9 square roots of 3 minus square root of 3. Is that true? Yeah? Okay, so what's 9 square roots of 3 minus square root of 3? That's not a trick question. It is 8. 8 square roots of 3 times pi, right? Because there's a pi out here in front. So that ends up being the volume for this one. Okay, is everybody good with that? Yes? Okay. Okay, so same equation, right? Y equals square root x. And just like we just spoke about, Hannah, it's going to be the same picture every time too then, right? Bounded by the same places and everything so that I don't mess things up. We will start by making that picture very clear. So 0 to 3 and square root of 3, and we'll shade in the picture. And then it depends how we draw, the way we draw our representative rectangle will depend on how we're rotating. On this one, and this is the part where we didn't go and look at his videos, right? We didn't look at rotating about anything besides x and y. So I'm going to show you how you rotate about things that are not x and y. So this is a different line, but it's still a vertical line. Agreed? Okay, so we're going to draw a vertical line, and we're going to draw that vertical line at 3, x equals to 3. So here's my vertical line that I'm going to rotate around. Okay? So how will my representative rectangle be drawn? Like the last one, right? It's going to be long and skinny, yeah, because it's perpendicular. So my representative rectangle gets drawn like this. Okay? Which means that this is delta y, yes? Which means I'm doing my integration from what number to what number? 0 to square root of 3, because it's around the y-axis here. I'm going to have dy whenever I do, in fact, get done. It's going to be dy. I always have pi at the very beginning, yeah? And I need to find out my different radius, okay? Now, this is a little trickier than the last ones, than both of the last ones finding these radius. Whether there's one or there's more than one, it's a little trickier when you're not going around the x-axis or the y-axis. So my radius is really right here, right? If I spin this thing, it's going to end up looking something like a bowl. Yeah, a bowl. It's going to be a little bit pointy on the bottom or the top in the image here of the bowl. But it's going to look something like a bowl. And the radius of the bowl goes from my blue line here out. From where you guys are sitting. Yeah, I did it the right way. From where you're sitting. Blue line out, yeah? And so this is r of x. But this r of x, or it's not r of x, but r of y, isn't exactly my equation. My equation actually gives me this distance over here, doesn't it? Because the distance I just marked in red is the distance x, and x is equal to y squared. So how can I find the distance that I marked in black? Because I don't really want the distance in red. It would be 3 minus x, right? The whole distance is 3. The little distance in red over here is x, so if I do 3 minus x, I have the piece in the middle. So this piece right here is actually 3 minus x, but again, I don't have x. I mean, I don't want this in terms of x. X is equal to y squared, right? So my radius, and this is a disk, this is not a washer, right? Because there's not an inner and an outer. This is one solid bowl when I'm done. Okay, imagine your popcorn bowl turned upside down and it's filled in with goo. I don't know, something, because it's got to be full for it to be a volume. Then what I actually have is I actually have my radius of 3 minus y squared. That's my radius. And then the formula says I need to square my radius. Now, do not be misled. That is not the same thing as 3 squared and y squared squared, right? There is no property that distributes exponents. So you would actually have to either physically multiply this out with foiling or recognize the kind of multiplication that this ends up being. And if you recognize that, this ends up being 9. It's minus 6y squared and plus y to the 4th. If you have to see it written out to know where I got that, that's fine. Just write down, I need to do 3 minus y squared times 3 minus y squared. Right? First terms gives me 9. The middle term and the outside term, the inside and outside give me 3 each. That's 6, negative 6, and then the last one gives me y fourth. Everybody good with where that came from? Okay. Like I said, you know, the setting it up, recognizing what the radius is the hard part. Because this is easy to integrate, isn't it? Most of you did this about 6 months ago well, at least you did it 6 months ago when you took Calc 1. So we're going to integrate this now. Oops, this is 0 to square root 3. All right, so what is the antiderivative of 9? 9y, thank you. And then 6y squared? It is 2y to the 3rd. And then y to the 4th? 1/5 y to the 5th, or y to the 5th over 5. Good. And then we're evaluating that at square root 3 and at 0. And you guys should be loving the fact that you got a 0 in the problem, right? Because when I put 0 in everywhere, it's just 0 on this. Okay, and it will be for all of our examples on this particular problem. So I've got 9 square root 3. I've got minus square root 3 cubed. And then I have plus square root 3 to the 5th over 5. And then I have minus 0. I'll just put it in to make sure that you recognize that it is there. It's just 0. All right, so we have some square roots again. I have 9 square root 3. What is 2 square root of 3 cubed? Yes, so right now I have 9 square root 3 minus 6 square root 3, for the same reason as the previous slide. What is square root of 3 to the 5th? 9 square root of 3, and then that's also over 5. Okay, so if I had my notes, I would be able to just tell you what this number is, and I don't. So I think I have my calculator. Somebody's going to grab their calculator for me. I want you to take 9 minus 6 plus 9 over 5, and then turn it back into a fraction. So I'm ignoring the square root 3 because it's in all of them. Okay, so I want you to take 9 minus 6 plus 9 over 5. Did it turn it back into a fraction for you? You did that?
I did it.
Okay, so 24 over 5. Is that what you have, Hannah?
24 squared is 3 over 5.
Perfect. 24 square root 3 over 5. Thanks, Cameron. I'll just let you do it next time.
They do more complicated sometimes.
Okay, everybody good with that?
And then should I have pi?
Yeah.
Yes, thank you. I did leave that off. You bet. It does need the pi in there. Okay, so that's a different axis. Now we're going to do a different axis yet again. This axis, same region, is still a vertical axis, but it's further out, which changes things. All right? All right. There we go. So we have our same original image that we had before, from 0 to 3 and 0 to square root 3. And here's my picture. Oops. But the difference is, of course, we said that our axis of rotation is out here at x equals 6. Okay, so when we rotate this one, do we get a disk or a washer? This one gives me a washer. It's hollow on the inside because there isn't any piece of this graph between 3 and 6, right? It's going to create a big empty space in the middle. Everybody with me on that? Okay. Now, that changes the equation and it changes the work we do a little as well. So my volume is pi. My representative rectangle, of course, looks like this. That's still my representative rectangle for my actual image. And so I'm still doing this in terms of y. All that good stuff's still happening because dealing with square root of 3s are so much fun. So we need some more of those. And as we're looking at this, then we need to figure out what the outer radius is. And it's not quite the same as it was on the last problem. My outer radius is all of that, isn't it? So how do I get my outer radius? Last time it was 3 minus x. What is it this time? It is 6 minus x, right? This distance over here is still x. But the distance all the way out to the blue line is now 6. So I have 6 minus x, and as we established before, because this is y equals square root of x, x is equal to y squared, right? So my outer radius is actually 6 minus y squared. And then I'm squaring that. What is my inner radius? What is it, Aaron? It is 3, yeah. It's just the distance between 6 and 3, right? It's this piece right here. That's my inner radius, and it's 3. So minus 3 squared, and then all of that we're going to integrate. I don't want to integrate it as it is, though, because I can clean up a lot with some algebra. So this is 0 to square root 3. I have 36 minus 12y squared plus y to the 4th when I FOIL that out, and then minus 9. One more step to simplify before I actually do any calculus. You guys recognize you haven't done any calculus yet, right? I suppose you could say the setting up of it was a little bit of calculus because you've got this calculus notation. But we have 36 minus 9 here, which is what? 27. And then I have negative 12y squared and y to the 4th. Now we get to do the actual calculus computation anyway. Yeah, we haven't computed anything. Oops, that's square root 3 left out. All right, so antiderivative. Somebody tell me the antiderivative of 27. 27y, because we are dealing with y's, right? 27y. What's the antiderivative of 12y squared? Good, 4y to the 3rd. And then the antiderivative of y to the 4th? Y to the 5th over 5. And I get to do my derivatives, limits of or my antiderivatives, limits of integration, square root 3 and 0. Okay, so we have pi. I have 27 times square root 3 minus 4. What is square root of 3 cubed? We did this just a minute ago. What happens when we do square root of 3 and then we cube it? It's 3 square roots of 3, right? And then what did we get when we did square root of 3 to the 5th? Cameron, you want to do that in your head? Square root of 3 to the 5th. That's it, Emily. Good job. 9 square root of 3 and then over 5, right, Emily? Yeah. And then we've got square root of 3 in every problem. So either Cameron's going to do it in his head or somebody's going to grab a calculator. We're going to do 27. Right here, 27. We're going to do minus 12. And then plus 9/5.
I got 114. Square root 3 over 5.
114? That sounds large, but it could be. I don't know. Maybe it is. What'd you get, Hannah? Oh, it's even bigger. 124. You're very close, Cameron. You're off by 10. 124, square root of 3 over 5. And then we will remember our pi this time. Is that good? Are you with me? Okay, we have one more. Can you last? You guys can do it. Same directions, of course, right? Same equation anyway for the direction. It's y equals square root of x. Picture starts out the same region anyway. And we've got going out here to square root 3, not square root 3, 3, up here to square root of 3, and here's my region I'm rotating. But this time I'm going to rotate around a horizontal axis, and I haven't done this since the very first problem on this assignment, right? Here's my horizontal axis of rotation. It's down here at y equals -1. Okay, so let's draw a representative rectangle. How will it look? It's going to be vertical this time, right? Because it needs to be perpendicular to the axis of rotation. So there it is, right there. Is this a disc or a washer? A washer. Very much like the last one, actually, right? Because it's actually a constant hollow piece in the middle. Because I'm going to be hollow from 0 down to 1, -1. All right, so this is a washer. I end up with the volume equals pi. Am I integrating with respect to x or y on this one? X, finally, we got to go back to x, right? Because this is delta x. Yeah? Yep, this little distance here, these skinny little pieces in terms of x. This is a washer, though, so, and x goes from 0 to 3. Let's put that in. We don't have any square roots on this one, so that's friendly. Well, we don't have any square roots in the limits of integration. So what is my outer radius? Because you guys said it was a washer, or at least some of you who are talking to me right now did. What is my outer radius?
1 plus x.
Close.
X.
1 plus y, which is the square root of x, right? It's 1 plus the height, and height is a y distance up to here. So this height is actually 1 plus y, and y is the square root of x. So that's my outer radius. See, I told you we didn't exactly get rid of the square roots. We just got them in a different spot. So I have 1 plus the square root of x for my outer radius, and that's squared. And then what is my inner radius? Yeah, it's 1, right? It's this distance right here. So this is minus 1 squared. Okay. So we get to square something with square roots in it now. And I know that you really want to just distribute that square, but you still can't. Okay? Still can't. Still have to FOIL. So this is pi from 0 times pi from 0 to 3. I end up with 1 plus 2 square root x plus x, and then minus 1 dx. Okay, that's again from FOILing out, right? All right, so I can cancel my 1s. That's something, yeah? I have minus a 1 and a plus a 1. So this is from 0 to 3 of 2 square root x plus x dx. All right, so what's the antiderivative of 2 square roots of x? Well, it has 2 in it now. What?
Six. 6 over 2 to the x to the 2/3.
You're thinking along the right lines. It's not x to the 2/3, though.
I mean, 3 halves.
3 halves. Okay, so right now the power is 1/2, right? So if we increase the 1/2 power by 1, we get 3 halves. So this would be x to the 3 halves. And then we divide by 3 halves, or we would multiply by 2/3, which we'll do in a minute. What's the antiderivative of x? This is the easy one. Somebody say it. Thank you, Dylan. X squared over 2. And we're going to evaluate this from 3 down to 0. Again, I like my zeros. All right, so the square root of, x to the 3 halves, just as a reminder of what this is actually the square root of x cubed, isn't it? Which is the same thing as x square root of x, right? Kind of like we did with the 3's just a minute ago, yeah? So right now, and I'm going to divide by 3 halves or multiply by 2/3, so this is 4/3. And I have the number 3 square root of 3 because it's x square root of x. Plus, and then I've got 3 squared, which is 9 halves. Now this is different than the other ones we dealt with a little bit ago because I can't combine these two terms together. Why not? Yeah, that's right, Hannah. I don't have a square root of 3 in that second term, do I? So I'm not going to be able to combine them. So when I write this, I would write the pi on each term. So this would actually be, looks like 4 square roots of 3, doesn't it? Unless I made a mistake, 4 square roots of 3 pi plus 9 pi over 2. Or if you want to leave the pi on the outside and write it as 4 square root of 3 plus 9 halves, that's fine as well. Any questions? Okay.